Hello again. Welcome you to the Calculus Conundrum series on limits. And I call myself the Perfect Square, and feel free to subscribe to my video if you find these helpful. In this video, we're going to talk about evaluating limits directly. Now, all of those in the first video, I could not evaluate them directly because you might remember that for each one of those examples in the first videos, you ended up dividing by 0. But that's not going to be an issue here. We will return to those videos a little bit later, and I'll show you how to evaluate them. But in this video, we're going to focus on just directly evaluating limits. Now, I'll start you with some properties here. The first property is the limit of b, where b is a constant, as x approaches any number, is always b. So the limit of a constant function, so let's say you want to take the limit of the function 5 as x approaches -2. Well, it's going to equal 5. And so the limit of a constant is just going to equal the constant. And it doesn't matter what x approaches, the limit of 5 as x approaches 10 would be 5. The next property says that the limit of x as x approaches c is just c. So in this case, since the function is x, then when x approaches c, the limit will be c. So here I have the limit of the function x as x approaches 15, and that's going to equal 15. And then the limit of x as x approaches -3 is going to equal -3. So again, if the function is just x, the result is going to be whatever x approaches. Now, here it says the limit of x to the nth power as x approaches c is c to the nth power. So that just means that if I have the limit of x to the third power as x approaches 2, then that limit will equal 2 to the third power, which is 8. Or if, let's say, I had the limit of x to the fourth power when x approaches -3, well, then that will just be -3 to the fourth power, which is 81. And we also have a similar limit for the nth root. So the limit of the nth root of x as x approaches c is actually the nth root of c. So for instance, if I want the limit of the fifth root of x as x approaches -32, then that would simply be the fifth root of -32, which is -2. Now, you can't always simplify these radicals. Like in the next one, it says, what's the limit of the cube root of x as x approaches 7? Well, that would just be cube root of 7. And you can't simplify cube root of 7 unless you write it as unless you approximate it as a decimal. So I'm going to leave it in its exact form, cube root of 7. So here are some more. This is just reiterates what I just showed you. If you take the limit of x as x approaches 11, you're just going to get 11. If you take the limit of x cubed as x approaches -4, you're going to get -4 quantity cubed, which is -64. If you take the limit of the square root of x as x approaches 11, you're going to get square root of 11. And if you take the limit of the constant 37 as x approaches 11, you're simply going to get 37. Now, next we have a few operations on limits. This first operation just says that if you take the limit of a constant times f of x as x approaches c, that's the same as taking the limit of f of x as x approaches c and then multiplying it by the constant. So in other words, if I wanted to take the limit of 3x squared as x approaches 2, I could take the limit of x squared as x approaches 2 and then just multiply it by 3. So that would be 3 times, this limit would be 2 squared, because we saw this property in the previous, well, up above. So we'd have 3 times 2 squared, which is 3 times 4, which is 12. Now, this is really two properties. It says the limit of a sum is equal to the sum of the limits, but it also covers the difference as well. The limit of a difference is the difference of the limit. So over here I just gave one example using the difference. So here the limit of x squared minus the cube root of x as x approaches -1 is actually the same as the limit of x squared as x approaches negative 1 minus the limit of cube root of x as x approaches negative 1. And so the limit of x squared as x approaches negative 1 is just negative 1 squared, which is 1. The limit of cube root of x as x approaches negative 1 would be negative cube root of negative 1, which is negative 1. So you'd have 1 minus negative 1, which is 1 plus 1, which is 2. Now here I have the limit of a product is the product of the limits. So here the example for that would be like the limit of x cubed times square root of x. That would equal the limit of x cubed times the limit of the square root of x as x approaches 4. So the limit of x cubed as x approaches 4 would be 4 cubed. The limit of square root of x as x approaches 4 would be square root of 4. So I'd have 4 cubed, which is 64, times the square root of 4, which is 2. 64 times 2 is 128. Now, there's also a property for the limit of f of x divided by g of x, and the limit of a quotient is the quotient of the limits. Now, there's one thing I left off on this one. As long as this limit that I'm circling doesn't equal 0, then this would be a true statement. So just keep that in mind. So the limit of x cubed divided by square root of x would be the same as the limit of x cubed divided by the limit of square root of x, and of course as x approaches 4 in both cases. So the limit of x cubed as x approaches 4 is 4 cubed, and the limit of square root of x as x approaches 4 is square root of 4. So in this case you get 64 divided by 2, which is 32. Now the next couple, they might appear to be similar to ones we had up here, like C and D that we had up here. But up here, these were just for x to the nth power or the nth root of x. But these two, this is for finding the limit of a function raised to the nth power, and this is for finding the limit of the nth root of some function. So we'll take them one at a time. The limit of a function raised to the nth power would be the limit of the function and then raised to the nth power. The n's kind of hidden there, but there's an n there for the nth power. So what that means is if I wanted to take the limit of x squared minus x to the 5th power, I actually could take the limit of x squared minus x as x approaches 2 and then raise that result to the 5th power. So, and you know how to do this. You know if you take the limit of x squared minus x as x approaches 2, you just get 2 squared minus 2, and we would raise that result to the 5th power. So that would be the same as 2 squared minus 2 is 2, so that would be 2 to the 5th power, which is 32. And then this next one, the limit of the nth root of a function is the nth root of the limit of the function. So here I have the limit of the cube root of 5x minus 3. Well, I can write that as the cube root of the limit of 5x minus 3 as x approaches 5. And so now just plug 5 in and you get 25 minus 3 is 22. So since we have the cube root of that, the result would be the cube root of 22. Okay, well, if you put all those properties together, it actually allows us, if we want to take the limit of a polynomial as x approaches some number c, that would just be the polynomial evaluated at c. So we don't have to break the polynomial up into a bunch of terms like we did up there. So if I want the limit of this polynomial as x approaches 2, then all I have to do is plug 2 in for each of these terms for x. So that would be, the limit would be 2 to the 4th plus 2 times 2 squared minus 2 plus 5. And that turns out to be 16 plus 8 minus 2 plus 5, which is 27. And then also you have a similar property for the limit of a rational function. The limit of a rational function can be found by just evaluating the numerator at what x approaches. So evaluating the numerator at c and then evaluating the denominator at c. And again, as long as the denominator does not equal 0. So an example of that would be if I wanted to evaluate the limit of x squared minus 5 over x plus 3 as x approaches -1, I would simply evaluate x squared minus 5 at -1, so that would give me 1 minus 5, and then I would evaluate x plus 3 at -1, and that would give me -1 plus 3, so that would give me 1 minus 5 is -4, -1 plus 3 is 2, and -4 divided by 2 would give me -2. So I want to finish with just a few examples here. I'm going to just go over these kind of quickly, but you can slow the video down if you need to and go back over it. But the limit of this trinomial as x approaches -2, just plug -2 in for x everywhere there's an x, and then evaluate that, and you'll get the answer 23. And then here's the limit of a rational function, so as x approaches 1. So just put 1 into everywhere you see an x in the numerator, and then plug 1 in everywhere you see an x in the denominator, and then evaluate that, and you'll get 5 divided by 3 for the answer. Now this one is it's an example of the function raised to a power rule. So if I take the limit of 2x minus 4 to the 4th power as x approaches 3, I can actually take the limit of 2x minus 4 as x approaches 3 first, and that would give me 2 times 3 minus 4, which would be 2, and then I can raise that result to the 4th power. So I can do the power last. And then this one is an example of that nth root. So the limit of the cube root of 2x squared minus 5 is actually the cube root of the limit of 2x squared minus 5 as x approaches -3. So just plug -3 in for x, and you're going to get 2 times 9 minus 5, which is 13, and then you're going to end up with the cube root of 13 for the answer there. And then it turns out that when you take the limit of trig functions, all you have to do is evaluate the trig function at what x is approaching. So if I want the limit of sine x as x approaches pi, that would simply be sine of pi. Now this is true for all 6 of those trig functions. As long as you can evaluate the function at what x is approaching, you can just plug that into the function. So sine of pi, as we know, is 0. And again, on these last two, if you're not in a Calculus 1 class, you can probably skip these since they involve trig functions. And then the last one says the limit of tangent of x plus 1 as x approaches pi over 4. Well, that would simply be the tangent of pi over 4 plus 1. And then you figure out what's the tangent of pi over 4. I believe that's 1. And then so you would have 1 plus 1, which equals 2. Now let me wrap this video up by giving you a strong warning. Every limit that I evaluated in this section could be evaluated directly. But when we discuss limits, you're actually going to run across quite a few limits that cannot be evaluated directly, and you have to use some clever trick to evaluate them. Okay, so if you go back and think about the limits that I had in the first couple of examples, remember this, I could not evaluate the limit of this function as x approaches -2 because I got 0 over 0, and I couldn't evaluate the limit of this function as x approaches 16, again because I got 0 over 0. So we're going to have to find some way to replace these functions with something else, and that something else that we're going to use to replace those functions is actually going to come from the replacement theorem. So I'll talk about the replacement theorem in the next video.